Welcome to R-SAS Programming, Stat 40, Lecture 2. Today we're going to talk about R-Basics 1 is what we're calling this. And then next week we're going to talk about R-Basics 2. And after that we have SAS Basics 1, SAS Basics 2, and then we're going to get into the mixed lectures where we talk about a concept and then apply that concept in both R and SAS. And so right now we're really setting up some of the things that are unique to R. And what's really unique to R relative to SAS is this concept of data structures, and then some nuances between R and SAS in the development environments, how to execute code, code style, writing comments, little things like that that are different between the two languages. If you understand some of those differences, and then if you understand sort of the nuances between the different data structures between R and SAS, SAS is really just about data sets for the most part. There are some ways to make smaller structures in that, but R has much smaller data structures that sort of build up to being what we would consider an analogous structure to a SAS data set, which in R is called a data frame. So getting some of this early stuff out of the way is really important, and that will help us move forward with the exploration of just concepts and then looking at it in two different languages, the R and the SAS language. The development environments available to you in R. First of all, when you download R, you're going to get the what's sometimes called obviously just R or base R or R GUI software. So that's the standard development environment that you get, and the main piece of that is the console. So if you open up R, you get this look over here where you have a console. You see this little greater than symbol in red. That's where you're going to be executing your code. Let me open up R here and I'll show you. Okay, so here's the console. I can change the size here. There's a lot of different options you can do. You can change the colors. You can change the size of things. You can open up graphics windows, open up new documents, which are, you can write R code into those new documents, all these things. And I'm using a Mac right now, but there's pretty good carryover when looking at the Windows environment as well. And of course you have these options up here, and actually there's options up here that will kind of have some wizards for importing data, R code, setting and changing your working directory. We'll talk about that concept next week in terms of actually obtaining outside data. This week we're just going to really create some data structures, some fundamental building blocks in R. I think that this is really something that gets passed over too much in introductory R courses, because everything you end up doing in R, you're going to be, most of the time, creating, referencing, manipulating a data structure. And R functions return data structures. And if you know what kind of a structure each function is returning, you can manipulate that structure, reference that structure, take out the pieces that you need from that structure when you're doing a variety of analytical activities inside the R environment. Okay, that's enough on that one. So anyways, the console though, here we can just execute code. Let me zoom back in a little bit. So I can just type code here. I can just say hello world as a character string by putting these quote marks around, and it'll just return an object. I've just asked it to print this character string, and it just returns an object. This little 1 just means first object in this data structure, this character string. It's actually a character vector of length 1. We'll talk about that today. But it just returns just this one piece here. And if I have multiple strings, say I want to combine A, B, C, then it returns A, B, and C. And this 1 means the first object here. So the first one is A, and then the next one's B, and the next one's C. Let me show you how that works if I'm actually asking for a series of numbers where I'm going to have to need multiple lines. So I can also ask the system to print the numbers 1 through 100. And so what this is doing is, so this is a little range identifier. Obviously, I wouldn't want to say 1 to 100 like that. That's why the R system, mini systems, Microsoft Excel, they all use this colon to identify a range of values. Because obviously, the minus sign is already taken, but a lot of people use that. Or a mathematician may use, brackets with a comma or something like that to identify a range. We just use this colon here. So I want values 1 through 100 printed. I hit enter to execute in the console here. And I see that 1, this little 1 row, that's showing me, the next row is not 2 because it's not showing me rows. It's actually showing me what the first, the index of the first object is within this structure here. So 1 is here, then 2, 3, 4, 5, all the way to, here we can see that the 15th object starts here. So I know this is the 16th object. This line starts with the 99th object, and so I see 99, then 100. Obviously, this is just a number 1 through 100, but if I had something, 2,000 to 3,000, then it would get kind of complicated to read. And so I would say, where am I at? What element am I looking at any given time? And so if I wanted to find the 910th element, I would say, okay, 903 starts here. So this one right here is 903. Okay. So this is 904, 5, 6, 7, 8, 9. There's a 910th element. So that's how things are kind of printed in R. Let me just quit R. Okay, there's also an integrated development environment called RStudio that we'll be using in this class. RStudio is actually a company, and they make this. It's also a free and open source piece of desktop software, as is base R software. And this company creates this free version, really, and it's got a lot of great tools to it, like syntax highlighting, auto code indentation, auto ending brackets, code completion, real-time function parameter list. As you're typing a function, it says down on the bottom piece, the parameters that are available to that function. Even lets you know that you spelled the function correctly, lets you look up functions very easily to use, because a lot of times you'll forget what all the parameter names to all the functions are. You'll forget what the function names are for the things you want to do, and you'll definitely forget, the parameter list. So it's nice to have the parameters available like that. There's also utilities to send code and functions to the R console. And some of these features are starting to be integrated into the base R software as new versions are unleashed, but it's still got a lot of great tools. I'll kind of show you some of those by opening this up. And so for one, we just get one screen here, and we can rearrange these different boxes here. And so I have different objects I can view down here, like a plot will pop up down here. I have information about what's in my environment, different objects that are in my environment. I can open multiple code programs, R programs here, and it'll just have a bunch of tabs just like a browser window would have. So I can have a bunch of tabs open. I can run different pieces of different ones, and they will execute down here in the console. So here, this is that same console. Here's my little blue greater than sign now. And so here I can do the same thing. I can say hello world. This is just a character string. It's actually a vector of length 1. And I can see hello world pops up. I can say 1 through 100. I get my numbers. I see that same kind of system, 93. Here's 93rd object. And so on. So this is a nice, you can start to see why it's called an integrated development environment. If I start to assign object names, we'll talk about that in a bit. I can see in my global environment that I have an object now called X. Okay, so it's kind of nice to see what objects I have here. Oh, and it even tells me some information about that object that's in my environment here. So if I go to reference X later in a piece of code, like I say I want the average of X, notice also the mean function popped up as I'm typing it. I type mean, there's all these functions available to me that start with the word mean. I just want the regular mean function. So this is pretty nice to have. Here, I actually just typed the left parenthesis and the right one already showed up, so that saves me some time too. And then I just say X, and I can hit return even though my cursor is not on the outside of this parenthesis. I can hit return and it'll already just move to execute that. Also note, this is really nice. So if I want to know, if I want to nest functions, I want the length of the mean of X. This is a really boring function because it's the length is going to be 1. There's just one object that is the mean of X. It doesn't return a longer object than that. It's a vector of length 1. But watch as I move my cursor. I move it to, I'm not sure how good that's going to show up on the screen, but I move it to the outside of this left parenthesis. And as I move it inside, I can see that that parenthesis corresponds to the far right parenthesis. It's kind of putting a little gray shadow on it. And so I can see where my where the opening bracket is to my closing bracket and where the closing bracket is to my opening bracket. So I can track things very easily. Okay, and I knew that was going to return just a 1. Okay, so it has a few just little things that that really add up to make for a much more pleasant development experience. I want to talk about help statements. So in R and RStudio, which by the way, RStudio is just one of the more popular development environments for R, other than the base version. There's others that are available that other people use for different reasons, and I think RStudio is going to be good for the purposes of R-Class. It is also easily for free download, as are some other integrated development environments for R, but it's also pretty popular. I think it's got like 1 million downloads, and that's also great because if you go start working somewhere, you're going to want to at least know how to use some of the more popular ones, right? And then you can kind of, if your workplace uses a different environment, you can kind of learn that on the fly. So, okay, so help statements. If we type a question mark, like I used that mean function earlier, so if I do question mark mean, I'll see the, arithmetic mean. Okay, so that's a description of the function. And I can see I'm in the R documentation here. And so this just pops up and it says arguments I can pass in, X. So X is just saying, mean X. X is just something I can pass in, a parameter I can pass in. I actually had an object called X, but that's not, it can be an object called anything, right? I can have an object called, I don't know, numbers 1 through 10, mean of numbers 5.5. Okay, I can also say, that's a positional parameter call on the function. I can also say mean of, and then I can say x equals numbers. I'm saying that first parameter, instead of just using positional, we'll kind of talk about this a little bit more later too, but instead of using a positional parameter call, I can use this named parameter call. So I'm saying that x equals. And then if I wanted to use these other arguments available to that function, or arguments also known as parameters, available to that function, I can see that I have trim, NA, remove, things like that. And there's defaults. See, defaults are set up. So there's no default for x. I have to put something in the first parameter slot. But trim is default to 0. NA remove is default to false. So I don't need to specify these. I can just specify any numeric in here, and it'll get the mean for me. Okay, so that's just the question mark mean to get that information. I can have other specific subjects I want to look up the documentation to. Well, if I don't really know necessarily what I'm looking for, I can use 2 question marks and say mean. And that's just going to do a larger, broader search of the documentation out there. And so now I can see that mean shows up. This is that documentation I was just looking at when I said question mark mean, because I went right to that exact topic. But now I've kind of searched topics for just that string of mean. Okay, so I get different I have different information returned to me. Okay, so I have just documentation that contains mean, or information about the mean, or using mean, or anything like that. And then I can also use help start. So if I type help start, open bracket, close bracket, so it's just like a parameterless function call here, then it'll open R technical manuals in your browser. Okay, so it'll pop up a new browser tab or whatever if you have a browser open right now. Then it'll just open up just the sort of that R core team has put together some technical manuals on R that you can read. Those are kind of hard to digest sometimes, and sometimes you'll get better results just Googling a specific problem. If you have a specific problem and you're going through, then that's going to be sometimes tough to track down in the technical documentation, or maybe you want to see an example right away instead of just a real technical explanation. You may try different blogs, and there's a lot of good resources out there. Something I do use a lot is the question mark, and then a lot of times I'll use a function name, and I can see what parameters are available to me that way. Okay, let's talk about evaluation and assignment. Evaluation of code and assignment of objects, that is. So code evaluation. So R evaluates code line by line, top to bottom, as we would expect. Each complete statement that is sent to or typed to an R console is evaluated. Most statements are either assigning a name to an object, which we call assignment, or returning or printing an object. Okay, so you saw when I had R open, I was, if I say X is, I keep being boring here with I'm not very creative right today. I'm assigning now X to be values 1 through 10. And now by just saying X, I'm implying that I would like X to be printed. So I hit enter, it's printed now. Okay, so I have a statement that's assigning something using an assignment operator, or it's printing something. Okay. So another thing you can use is the explicit print function. Sometimes you need to use that, and I'll say when here in a little bit. But you can use this explicit print function, and it'll do the same thing. It'll print X, okay, which is values 1 through 10. Let's talk about statement evaluation. Okay, so we can write everything on one line in the console, as I've shown here. So X, I'm assigning that the value, the sum of Y. Okay, so whatever the sum of Y is, I'm assigning that to X. If I don't put the closing bracket on there, then R automatically pops up with um, um, a little plus sign here, and then I can decide to put the closing bracket on or not. So, well, I mean, I'll have to put a closing bracket to get a complete statement. Okay, so it's not a complete statement yet. So let me make y, I don't know, 2 through 20. And I can see that the sum of y is 209. And I can assign x. So this will overwrite the x I have there now with the sum of y. But let me delete the ending parenthesis here. I'm just going to hit return. A little plus sign pops up. I have to put a closing parenthesis on in order for it to evaluate. So now I look at x, 209, as expected. That's the sum of y. Okay. Also, similarly, if I just put x and I put the assignment operator and I don't put anything else, I just hit enter, it's going to say, what do you want to assign? So I'm going to say sum y. Well, what if I don't put a closing parenthesis here? It's going to say, hey, you still haven't given me a complete statement. So I put a closing parenthesis. Now it's a complete statement. I go back to having this greater than sign. Okay. I can also execute multiple pieces of code on one line in the console. And so what I would do is I would just use the semicolon operator here. So I could say, I'll use that same example that I have on the slide. Y is 1 to 10, semicolon. See how I can keep typing now? X is sum of y. So I've defined y. I've assigned x to the sum of y. And now I've asked to print x. So I have 3 complete statements now on one line. Instead of that, sort of the opposite would have been the incomplete statements. So I had to use multiple lines. And now I've crammed a bunch of statements onto one line. I hit enter, and I get 55. Okay, which is the sum of the values 1 through 10. So this is not typically, some would consider this poor coding because it's less readable when you just cram a bunch of stuff onto one line. The space is free. I mean, that's kind of what I always say. You can use all these lines. The white space is not going to cost you anything. Okay. So that's statement evaluation. Objects, printing and assigning objects. First of all, we have to know that in R, everything is an object. Okay. And we've been defining here these little data objects. So we've been assigning those. We're generally either printing or assigning an object. And so here's some examples here. Using that assignment operator that we'll talk about next, I'm assigning this this named object here, 1 to 10. That's the name of it. I'm assigning that the values 1 through 10. I can also do multiple assignments. So I can say, I'll use my same example here. So X, I'll use something else like A. I haven't used that yet. And B, I assign those the value of 100. And so now I see what A is, I see what B is. So it just flows this direction, right, of the arrows. So basically it goes like this. It sees a 100, it assigns that to B. B is now holding a value of 100, and it sends that to A. Okay, so everything is set to 100 here, B and A. This is not very commonly used, but we can also do user input prompts. So it's not, like I say, it's not really common, I guess, unless you have a real, maybe you've created some automated program that people can open up and type a few things and then it executes a set of routines. Maybe you would need that. Anyways, here's another way of defining some objects. We can just ask the user for the information. So just, as with the example, I won't demo this one, but just as with the example, we have a greeting, and I said the greeting is equal to hello. I have your name is another object, and that's from readLine, so I'm using the readLine function. and the read line says, what's your name? And that's going to be the prompt that I put in the read line function. And so it prompts you and just says, what's your name? And then you just type your name. And then I'm using the paste function here, which just sticks these strings together, hello and your name, and then just says, hello Jared. Okay, so it's just a little, you can play around with that a little bit, but you do have the ability to prompt the user for input. We've talked about the object assignment operator, so it's this less than followed by a minus sign to make a little arrow so we can see what direction we're assigning objects. You can actually also use the equal sign, but it's usually considered best practice to use the arrow, and Google Style Guide, which we'll talk about here in a bit, also asks for use of the arrow and not the equal sign. And there's a few reasons for that. So the equal sign is also used to specify functions, and it's also used in conditional tests. So you're seeing you can test if something is equal, and that's either true or false, or something's not equal. It's used in there as well, and it's also used, like I said, to define function parameters. Like earlier here, it wasn't in this one I had open, but I can say instead of mean of a, well, it's going to return what, 100 because there's just one thing in a, but I can say mean the x parameter equals a. So that's a named parameter call. So I'm using an equal sign there, but I'm not assigning x the value of a inside of here. Sometimes it's harder to follow more complex code, what's being assigned, and so the assignment operator is used. Also note that you can use it on the left-hand side or the right-hand side. So I can assign things this way with a less than and then a minus sign, or I can assign things the other direction using a minus sign followed by a greater than sign. So in my example above, I assigned a and b the value of 100. I can also say 200 minus sign this direction, c minus sign this direction, d. So now c and d are 200. I typed d twice. I think it's more generally accepted best practice to do the left hand, this way that I've been doing it, this left hand direction here. Okay, let's talk about naming objects. Okay, so I've been naming them like X and Y and A and B and stuff like that. You can name them actually all the way up to 10,000 characters, so go nuts. Some older versions, if anyone's running an older version, you might want to look out for backwards compatibility issues because the old character limit was 256 characters. They can only contain letters, number, so like they have to be somewhere on the ASCII digit, scale. So it has to be like a normal, regular letter, not like some kind of a strange emoji or something weird like that. It's not going to pick it up. So you can look up valid letter choices. Pretty much anything on a standard English keyboard is going to work. Numbers can have a dot. So this little dot right here, period. Underscore is an acceptable thing to use, and you can't use spaces. Right, I can't, because it's going to take that as, I can't say X space Y and assign that 1 through 10. That's going to give me an error. So, I should also note that I use spaces here around my assignment operator, and that's considered just better code style. But, I wouldn't need that. I wouldn't need to add all these extra spaces here because I forgot. See, I forgot a space right here, and that's not a big deal. But spaces between, space in a name, you can't do that. So it can only begin with a letter, so it can't begin with a number. Okay, and it can only, so the first one just has to be a letter, then it can have as many numbers as you want. And it can begin with a dot, actually, as long as that dot is not followed by a number. Okay, so it's kind of a strange little nuance there. So if you have something like dot 2 and then some other letters or whatever, or other numbers, it's not going to work. And it cannot be a reserved word. So these reserved words are sort of off limits for you to find things. So I can't use if. I can't say if is equal to 1 through 10. I can't call an object if. Okay? Unexpected assignment. What it's saying is you've unexpectedly violated our rules here of assignment. And I found this information. If you want to look this up, you can use the question mark make.names, and you can look in the details section, and that gives you some information about valid names you can use. And then length restrictions, you can do question mark name, and look at the details section there to see the length limits. Next, we'll talk about code execution. So code can be executed by typing or pasting code directly into the console. So here I've been typing directly into the console. It can also be sent to the console line by line or by highlighted section from an R program or a program that's open in RStudio. I showed you how you can have multiple tabs open there, multiple R programs. From the R console, so I'm in base R now, I can choose this option here, and it says create a new empty document in the editor. And so here I can actually create an R program. You can see the lines. I can zoom in here a little bit. I can type here, okay, for an R program. And I can send that to the console. Okay, we'll talk about that in a bit. Also I'll say the source function can be used. So you can type directly in the console. You can have a program that's open, and send it to your console. And the third way is to use the source function. So the source function, actually, you specify a file path and an R program that you have saved somewhere on your machine. You put that inside of the source function as a parameter there, and it'll run that whole program at once into your console. Little nuance to note here is that the implicit printing that we've been doing, see, I just say X and it prints X. That's implicit printing versus explicit. I would say print X. If you have a program that you're going to source, it doesn't allow for implicit printing. So you're going to have to go through that program, and if you know you're going to source it using the source function, you're going to have to go out and go into that program, make sure that all your implicit prints are made explicit. So you have to actually have the print function written on those. Vectorized operations. In R, operations are executed in a vectorized or element-wise way. That means the first element in an object is matched with the first element in another object when some kind of operation, such as a mathematical operation, is performed. This also translates to two-dimensional objects, like a matrix. We'll talk about different objects here in a while, where the first row and the first column are matched. Then that element is matched with the other one when you're doing an operation. So I have examples here. So I defined Y as, I'm using this little C saying combine, some people call that concatenate, 2, 3, 4, and 5. Okay, so when I'm creating an object, I can't just say, if I'm doing a range like this, that's okay. Otherwise, if I'm just saying 2, 3, 4, it's going to throw an error, right? I have to say X is concatenate 2, 3, 4, 5. I think I had a 5 in there too, right? But in my example here, but if I have an object X and it has elements 2, 3, 4, and 5, I have Y, it has elements 20, 30, 40, 50, and I add those. So I'm asking it to print X plus Y. It'll give me 22, 33, 44, and 55. And so that's the first element gets added, 22. Okay, so this next element gets added, 33. Next element, 44. Next element, 55. Same as if I multiplied it. Okay, I'd get 2 times 20, 3 times 30, 4 times 40, 5 times 50 as a result. So let's say I made a matrix, so don't worry too much about the function I'm using here. We'll talk about that. But I create object A. A is a matrix. it has elements 2, 3, 4, and 5, and it's 2 by 2 matrix. Okay, so it'll be the top row will be 2 and 3, and then the next row will be 4 and 5. B is a matrix of 20, 30, 40, 50, 2 and 2 by 2. Okay, so these are really similar to our vectors now that they just kind of stacked on top of each other with 2 dimensions here. So now if I go A plus B, just like I did here, X plus Y, I get, again, 22, 33, 44, 55. Okay, and we can see that the first, I said it wrong earlier, so actually 2 and 3 is going to be the first column, 4 and 5 is going to be the second column. So I had 2 and 3 in the first column, I had 20 and 30 in the first column of the other object, B, and so it just went 2 plus 20, 22. Okay, these are in the same position. Okay, so these are both in position column 1, row 2. Those are 33, 44, 55. Okay, so that's vectorized operations in R. It makes things very quick. So instead of me having to specify A row 1 column 1 plus B row 1 column 1, then A plus, and so on, and build an object like that, we have these nice, neat vectorized operations that can make us perform, especially mathematical operations, much faster. Okay, let's do an R demo. R demo 1, code environments and code execution. So let me close R, and I'm going to go to RStudio, and it's going to be pretty similar between these two environments, executing code. So in this demo, I have this code available out on Blackboard. Just want you to gain some exposure in the environments and learn how to write and execute code in the console, send code to the console, and source it from a saved program. So kind of those 3 ways we talked about of executing code. So I have a program window open here, and I have a console down here. Okay, so I can open in RStudio. I can create a new file, or I can open a file using this button. And go to my desktop and open demo 1. Okay, demo 1's open. So we're going to run the code in R and RStudio. I've already been running code in R. I'll just focus on RStudio right now. In the console, so how do I run this code in the console? Well, I could type it down here. So like this first, these are comments in green, so these actually won't be executed. We'll talk about comments coming up. So if I want to find out what objects are available in my working space, I actually have to use ls. So what objects are available to me? I use ls. Character 0. Okay, that just means there's nothing in my workspace right now. There's no objects that I have stored in my memory on my machine right now. And then I can create a test vector called hello world. So I have a test vector. It's called hello world. I just copied and pasted it down here. I can also see in RStudio, it's kind of nice because it tells me, hey, in your global environment, you have an object called test vector, and the value is hello world. So there's a vector of length 1. Okay, I know if you've studied linear algebra, you're going to think a vector of length 1 is a scalar. It's still called a vector in R for simplicity. It's not called a scalar. Okay. Although you might see that written somewhere, that somebody is calling them scalars. That's fine. Vector of length 1. And now I can again print this ls function. I have print written here because I'm going to, I'm asking to print something out explicitly because I'm going to source this program later as a demo. So I've had to add these little print functions. Okay, so again, I can copy and paste this, or I can click in RStudio, I can click up here to run, and this will run. See, it says run current line or selection. If I don't have anything selected, it'll just run it. Okay, so it ran that print ls and told me I have a test vector object saved in memory right now. I can also highlight a section and run it. So I can highlight a section and click run, and it ran, everything I had highlighted. And if I hover over run, I also notice that it says, if I hit Command Enter, it's the same thing. So I can hit Command Enter, and let me just show you right here. So I hold down Command, I hit Enter, and it goes to the next line of code. And I can just keep doing this. I'm holding down Command and hitting Enter, and I can just keep executing this code. What this code does is it prints what I have in my directory, then it creates a test vector called hello world, and then it again prints what I have in my directory, so test vector should show up, that's there. And then I print the test vector, so that's actually going to return hello world, the string. And then I use rm to remove, so that deletes the test vector object, and then again I print my directory to see that everything's been removed from there. So let me start the program over here, and I'm just going to execute it line by line. Print ls, there's nothing there. Create a test vector called hello world, now print ls, test vector shows up as an object that's in my memory. I print the test vector, and it says hello world. That's what's stored in the test vector. And then I remove the test vector, and see it also went away in my global environment in RStudio here. And now I print again, and it says character 0. So that's just like empty. There's nothing there. Okay. I can also source this code. Okay. Instead of just executing it here from this program and sending it to the console, or pasting it or sending it, here's like sending it, telling it to run. I can actually just source it. So let me close it. Okay, I'm going to run that same program now in base R. So I'm going to open up R, and then I can just open up that program. Here. And then if I go to edit, I can see that I can execute using Command Enter. Okay, so I can do line by line. I can do Command Enter. There it's executing that line. And then I actually have to move down to the next one. Execute that line, that line, that line. Remove the test vector object. And now we'll see that I've cleared out my workspace here. I can also do chunks, so I can highlight a chunk and hit Command Enter. Same thing. See, also my comments got printed in there. Created that test vector. I can run all these lines here just like that. So I see that I printed that vector, then I removed it, and then I said, I'm ensuring that it's gone. Yep. Nothing in my workspace now. So the last option was to source a program. And so here I can go into R, and I can say, let's see, I think it's just source. Oh, source document. Let me open up a document window and say source document. It's not here. Oh, source file, sorry. Yeah, it's not source document, it's source file. I'm going to show you what this does. I may have to force quit. Okay, one more time. I'm going to open R. I don't need this one open. Source file. And then I want to source that demo program. Demo 1, open. And so it wrote this piece of code for me that says, it uses that source function that we talked about, and then it put the whole path and the program name here in parentheses. Okay, and so the first thing was to see what objects we have um, in our workspace, and there's no objects there. And then I create the test vector and then say what's in my workspace, and it says test vectors in your workspace. And then I ask it to print, and it says hello world. And then I remove it and then print my test what's in my workspace, and it says character 0. Again, it says no objects. So we had no objects. We created a test vector. We printed the test vector, and then we again have no objects. So this is just some very basics of, I could actually have typed this source function as well. And in fact, I can copy it, and if you ever forget like the exact syntax or your exact file path you want, it has that nice kind of browser setup. But I can source it right here into RStudio console too, or I can paste it into the console or into my program window here, run that line of code exactly as expected. Okay, so that's the sourcing an R program to run. Okay. Code style and comments. There's Google made an R style guide, and it's available online. I have the link down here. I just want to say that code style, indentation, spacing, layout, function, or operator choice, organization of the overall code, that's really important to the code developer, so you can remember what you're doing when you write something that's potentially thousands or tens of thousands of lines. You're going to want to know what the moving pieces are and remember why you did certain things that you did. So you're going to want to write notes to yourself, and then also to potential collaborators if you're collaborating on a project or that piece of code specifically, or those inheriting your code, operational project, process, ongoing project. The code a lot of time is a part of a larger analytical effort, and some sort of a marketing analysis you're doing, or you're doing some gene sequencing, or all these different things you could do. The code's just a way of doing that. You have other aspects of the project itself, reports that you build and things like that around it. And so you're going to want to have notes in there to others that may need to, maybe they're just somebody that reads the report and they want to just glance at the code real quick. Maybe they're not an extremely skilled R developer themselves, and so they want to just kind of read more human readable comments. Oh, this does this, this does that. Oh, okay, they can watch the data flow and how that occurs. But it also, really helps you with being able to hand something to somebody, having written it in a format and just a generally kind of accepted layout and way of doing things. And so, anyways, Google made this style guide. You can check it out at that link. This is what it looks like. So they give you different tips, and let me just look for some examples. So they talk about spacing, indentation, line limit. You don't want to have huge lines of code. They talk about writing comments that we'll talk about next. I kind of briefly touched on that. Yeah, and so on. So you just have like good and bad, and the bad's in red text. Anyways, take a look at that. I think it's pretty well accepted, not just within Google, but within the larger R community. This is pretty well accepted stuff here. So it also explains, okay, R is a high-level programming language primarily used for statistical computing and graphics. And again, this style guide here is so that R code is easier to read, share, and verify. Verifying code is somebody comes in and they want to see that it does what it's supposed to do, and when it's written in a clear, straightforward manner that they're used to seeing, they don't have to kind of overcome that barrier of seeing it laid out differently. It's kind of like if you're reading a book, you're used to the text going from left to right, and you're used to a certain type of sentence structure or whatever. But if you were reading something in some older form of literature, like you're reading like something from that Shakespeare had written. It's just going to take you longer to go through and read that. It's just not following some of the general English conventions that we use, and this is just some of the general R conventions that are being used. Comments. So writing comments is very important. These are non-executed statements. They're really just for writing notes, but they can also be used for masking the execution of certain lines of code. So if I put comments in front of a piece of code, then it's not going to execute. And then if I remove that comment, that little hash symbol, then it's going to then execute that part of code. So I could kind of like have a program where there's certain lines I don't want to execute sometimes, and then I can comment out some lines of code or comment some remove the comments from a line of code. But mainly for making notes, and it helps the program creator and future users of that program by allowing you can create headers and subheaders in your program. There's different ways to do that. There's different style choices that people use for making kind of like a clear like header section, subsection. Defining prerequisites and assumptions at the top of the program, saying, hey, this program's based on the assumption that you're hooked into this this data source already. You already have this connection built. Little things like that. Showing the user where to make changes. Saying, hey, you can change these things here and get this different result. So it kind of shows you, hey, there's some things you can modify in the code here that will give you different results. Describe what each part is doing. That's really the main use, is to say, hey, this is what I'm trying to do, and that helps people validate that it's doing what you want it to do. Explain why certain approaches were utilized. Sometimes you use like a non-traditional approach to do something. People may be tempted to change it to a more traditional approach, and you may want to kind of justify why you did something a certain way. Maybe there's a nuance in the data that means that you have to kind of utilize that non-traditional approach. These are some kind of abstract concepts right now about using comments. It really comes from just kind of my own professional experience, and you may not need to know much more than you can create headers and you can say what the parts of your code are doing. Some of this other stuff is maybe too much information right now. Let's talk about data structures. Oh, I also wanted to point out, so you can have comments on its own line or off to the side. So you can say anything after that hash symbol is not going to be executed. So I can make two of them. It doesn't matter. I mean, I'm not making a double comment or anything, but if you look at Google's style guide, they say using two makes it pretty clear where the comments actually start. You can see like two hash symbols much easier. It's easier to scan through and see where the comments are. Also note that in RStudio our comments were green. So that's a great thing about those development environments, where sometimes it changes the colors of certain items and certain they call that syntax highlighting. So I can also put it here on this same line, and so everything gets executed here just fine. X gets defined just fine, and then I can write something about X, over here, as long as it doesn't give me a huge line of code like Google was saying, 80 characters, and that's, you start to get really too long of a line at that point, so you could kind of wrap it to a different line. Introduction to data structures. So a data structure is just an object. We were saying everything in R is an object. You can think of everything as an object, but some of those objects contain data. Some of them, like in functions, contains data too, right? It contains code and contains metadata about the function, like the parameters that are available and stuff like that. But really, we're looking at the data that we're using for analysis. So data that we're using for analysis and that we're using for the purposes of statistical analysis or whatever it may be. That data, we call those data structures, those objects that hold data that we're doing calculations on and that we're combining together with other pieces and making summary reports on and things like that. That's our data structures. All objects can be combined into larger objects by extension. All data structures, which are just it's just kind of a convention to call things data structures that are these objects that contain data. Some people call them data objects. They can also be combined into larger data structures. So a data structure can be one or multidimensional. And the most basic data structure would be a vector of length 1 that we've talked about. Data structure classes. So you can have a class, like you can have a numeric or a character. You can have, and then there's other classes that we'll talk about. So if you have a vector of length 1 and it's just a numeric or a character, that would be a really basic data structure. And actually the most basic of data structures we call atomic data objects or atomic data structures. They have a atomic class. So let's talk about some of these atomic data structures or data objects. And so the atomic ones, the 5 most basic atomic ones are character. So that's like hello world is written out here. That's a character, and it's a vector of length 1. Although it need not be a vector of length 1 to be considered atomic. It's just got to have a basic uniform class. Okay, and so this is character value here. It's surrounded by these quote marks. Okay, we can have numeric, real numbers, including infinity and negative infinity, and so real values like 25. I could have also said like 25 point, any decimals in there as well. Infinity, I have a capital I on the infinity. That's considered a real value, a numeric value, I should say. And I could put a negative sign in front of that and it'd be negative infinity. I have special real values like pi, so I just type pi, and that's also available to me as a numeric. Next I have integers. So integers don't have the decimal places. It can be positive and negative, but I denote that as with this little L. And so this is a special type of numeric here where it doesn't have decimal places. So I just print this out and it just returns a 1. It doesn't have an L behind it. The L behind it just denotes it's an integer. I can also use different functions to convert things to an integer atomic class as well. The most common we'll be using throughout the class will be numeric and character by far. Complex, we'll have very little use for this. So these are complex numbers. So the real numbers, the numeric numbers, are a subset of the complex numbers because now we've added complex elements. So we have no real elements plus 1 imaginary element. And so this gives me, basically this is I right here. This is no real 1I. Okay. If you do, square root of -1, you'll get an error unless you change, your options, and you start working in this complex numbering system. So, and then you can also have logicals, true and false. You can write in all caps true or false, or you can just write a capital F or a capital T. And so here I wrote a capital F, hit return, and it's printed out false. Okay. You can also perform math on these true and false logicals because true gets stored in there as a 1 and false as a 0. So you could sum up a vector of trues and falses and see how many were true. You could say sum that vector. It's going to return a number, and that's how many were true would be that result. And that's actually useful functionality to have. There's also special data classes like NA is a missing value. It's a missing value for a character string, numeric string, any type of, numeric vector, character vector. That's your missing value, no matter what data type it is, no matter what data class it is, I should say. Just capital N, capital A. That's NA, that's a missing value. So if you have missing values in data that you're reading in, you'll see these NAs. That's not the same thing as not a number. Is kind of different. So that's a numeric value where I did something that didn't make sense mathematically, like infinity times 0, and you get NaN, not a number. Okay. Atomic data object classes. Let's see. So here I can make X as a character vector, and it'll have elements, I'll say A, hello, char string, B, C. These are just random, character objects. These are all individual vectors of length 1, but I'm asking to define x as this vector now of length 1, 2, 3, 4, 5. Okay, and so I say x, prints it out. I say is character x? True. I can do these little tests. Is it a vector? True. So it's a character class. It is a vector object. And I can say is atomic x? True. Okay, so it's atomic. Because it's all uniform of the same atomic class, then it can be not just of length 1, but of greater length and still be considered an atomic vector, really, of more than length 1. And atomic just means that it's a basic, homogeneous, all the same class of a basic atomic class vector form that can be used to build more complex data structures. That's all. We're just learning about what the building blocks we have available to us are. Okay, so that's an important little nuance to kind of understand there. So we have numeric vector and a matrix. So we can make a numeric vector, again, using that little C concatenation or combine function. We can print x, and we can add a dimension attribute. So this is a separate concept of attributes that we'll talk about more as we go on. But this is a metadata about x, and I can say give x a dimension of a 2 by 3. And then I hit x, and now it's converted that vector to a matrix. And I can reference individual elements with these brackets. So I want the first row, third column. First row, third column. And so first row, third column is a 2. And so it prints out a vector of length 1 being a 2. Okay, so this is just a way of, you can make a vector, you can make a matrix. We're just talking about some basic data structures here. Now there's a character vector and matrix that we can make too, so I can just make it right off the bat. Instead of adding a dimension attribute to a vector, I can just, there's many different ways to get the same end result. I can just take and make y, use the matrix function. Y is a matrix. It has elements A, B, C, and D, and they're arranged number of rows 2, number of columns 2. So here I named in row parameter of the matrix function in column, and it produces a matrix object, and I say y to print it, and I have A, B, C, D. Is it a matrix? True. Is it a vector? False. It's not a vector now. It's a matrix, right? We put a vector into here, but then we gave it dimensionality right away using the matrix function. I can reference objects. We'll talk more about referencing next week. I can say y. I can say, row 1, comma, and then all the columns. I didn't specify a column in this slot. So these are little squared brackets where I can reference individual pieces of this matrix. And now it returns A and C. So A and C were that first row. So I'm saying first row, all the columns, A and C, gets printed. Is that a matrix itself? That y first row? False. Is that a vector? Y first row? True. So the matrix is composed of vectors. You can see that the matrix is it has dimensionality to it. It has a more metadata about that object. So it's a more complex structure. So you can see how a basic structure like a matrix of some basic atomic class like character or numeric can be used to then form a matrix. Okay, so more basic object, more complex object. Here are some basic data structures. So we have vectors, matrices, arrays, lists, and data frames. These are just some basic ones, and we'll talk more about some data structures next week. How many dimensions is a vector? 1. A matrix is 2 dimensions. There's rows and columns. And now arrays are just kind of multi-dimensional matrices. So I just have n here. It can be any number of dimensions. We have lists, which are considered one-dimensional, and data frames, which are kind of like a matrix, and it's like a table. It's kind of like a data set in SAS. Actually, it's a tabular data, and so it has rows and columns. So it's kind of similar to a matrix in that way, but actually a data frame is a special type of list. Again, we'll get into some of these nuances more than just, this is kind of just an introduction here. So the component objects must be of the same class. For vectors, yes, they must be of some basic atomic class: character, numeric, integer, complex, logical. Matrices, yes. Arrays, yes. Lists, no. And data frames, no. So in data frames, obviously, we could have a column of character, we could have a column of numeric, and that would be just fine. We can have a column of integer, anything like that. That's fine for a data frame. That would make sense. In a data set or data frame, or tabular data in general, different columns can be of different data types, and we would expect that. And so lists are very similar, right? A list, if you wanted to make just a list of just holds about anything you'd want. A list is just kind of, if you just want to hold a bunch of things of different classes, you can just make a list. And it's got some properties that kind of, you could use it kind of like a vector, but it'd be like a vector that holds the value 1, 2, 3, and then a bunch of character strings like A, B, C, so you could just hold a bunch of things into that list. Default attributes, is there metadata available about that object? So there's null means no objects, so if you ask for the attributes of vectors, you'll just get this null. Matrices have dimension, arrays have dimension, multidimensional potentially, beyond 2. Lists, you'll get null in terms of the default attributes, and then data frames have these attributes called names, which are the same as the column names, and row names, and it'll also have an attribute of class available to it as well. So this is just something we'll talk about more, but this is like metadata about the data structure that comes in by default when you define just a basic one of these structures here. Okay, so we talked a little bit about null. Let's talk about null and empty objects. So null is an absence of an object. It's not a missing value. It would be a non-object. How did I write that? Not a missing value, be a non-object. I might change my writing there. So I can say A is null, and I print A, and I get null, and I say length of A is 0. There's nothing in A, but I've created just this empty object, this empty container called A. If I make something called B, and I say B has 1, 2, NA, 4, null, 6, and I print B, it just says 1, 2, NA, 4, and 6. That null is just not there. It's empty. Okay. There's also empty length 0 data structures you can make using functions like, if I want to create a vector, instead of using that little C concatenation operator like we've been doing, you can use the vector function, just like how we used the matrix function earlier to make a matrix. I can say X is vector and then just nothing in it. So I say print X, and instead of null, it says logical 0. And so it's assigned it by default a logical atomic class and said that there's 0 objects in that logical data structure. So that logical vector data structure. So now I say length of X, and that's 0, just like the length of A was 0. If I make a matrix, I say M is a matrix with nothing. It actually does something different than if I was to make a vector. By default, it gives me a 1 by 1 matrix with an NA value. And so I say length of M is 1 now. And so it's actually not an empty matrix. It'll give me empty vectors, but I can't do an empty matrix really. It gives me an empty, by default, it gives me not an empty one, but actually an NA, which is a missing value. Okay, and that's just a byproduct of how the matrix function is designed. I'm going to demo some more stuff here now. So our demo 2, creating vectors and matrices. Let's see, learn some ways to create vectors and matrices, gain some exposure to basic data structures and so on. Let's see. I'll just kind of briefly show you this demo, and then I'll have it available on Blackboard so you can just work through it, because I don't want to make this lecture too long. So I made kind of a fancy header here, just using comments. But I say part 1, creating simple vectors, and you can see different ways of creating vectors. And in the comments above each part, it labels, what each part is doing. So, take some time, read through this demo, um, look at how we can create with the sequence function from 25 to 49. That would be, the same as 25 to 49 here, So there's also functions where we can do sequences. We talk about positional versus named parameters. So I can say sequence 2549, or I can actually use the parameter name from equals to equals. And since I did that, I can switch the order. Since it's a named and non-positional call, those are the two types of ways to use functions. I can say 249 from 25, which is kind of weird, but that actually works fine too. And so this demo talks about that. I also have a repeat function where I can repeat 0 100 times. And so when I print x, I get 100 zeros. If I want to look up information about the repeat function, question mark repeat, REP rather. And then I can also repeat this little vector of length 2, 1, and 0 10 times. And so I get z is actually length 20, right? Because I repeated a vector of length 2 10 times. So I can use it to create data that way. I can repeat character string vectors just fine as well. I'm showing some ways of naming things. So since we can't use spaces in our object names, you can do alternate capitalization, or capitalizing just the first letter. So you can capitalize start of words, and see, we didn't use spaces, but that makes it easier to read. Okay, you can use dots, you can use underscores. These are all different ways of making object names with a bunch of words. And so you want to be specific. You don't want to have a huge, long object name, but you do want to be able to track what's doing what. So, and then also we make a logical vector. True, false, true, true. And look at the syntax highlighting here. It makes things pretty clear. We see that these are kind of this orange color here, and then characters are these red color here, so you can clearly see what's going on. But here we create a vector holding these values. We do some tests. Is it a vector? Is it a matrix? What are the attributes? What's the dimension? So anyways, take a look through here and step through this and just execute, a line at a time. Just send it. Maybe in RStudio would be a good place. So go to RStudio. And this will be like a nice easy way to do it. I can open my demo, and I can just execute one line at a time and read my comments and just see what's going on as I run each of these pieces. So I can just kind of take a look at each of these pieces. So you can see I made a matrix out of some values. Made another matrix. I replaced an element in the matrix. I made a logical matrix as opposed to a character matrix. So check that out. Okay, for Lecture 2 participation points, normally we wouldn't hand in the lab, but hand it in this time to Blackboard. There's an area to submit Lab 1, and it's due prior to our next lecture. I'll be a little bit maybe flexible on that by a few days because it took me a little bit to get this lecture out. So in R Lab 1, you're going to open up that program, download it from Blackboard under Course Materials Lecture 2. Write the R commands requested under the comments that define each section, and then when you're complete, save it and upload it to Blackboard under Assignments, R Lab 1. Let me show you what the lab looks like. It's very straightforward. So we have two exercises. Exercise 1, create numeric vectors. So it says part A, create a numeric vector called my vector. This part should contain 10 elements. So I would say my vector. It should contain 10 elements. So I can do any 10 elements I want. Okay, so I can do 21, 30. That would be fine. And then I can just execute that over in the console. I can, if you want to add some little extra piece on here, like you want to print my vector, that's fine. And then it says print the length of my vector using the length function, so I can say my vector 10. Okay, so I know I did it right. 10 elements. And then go through, and so that I already did A and B. There's C, and then there's exercise 2. There's an A and B. That's it. It's really straightforward. Just want to see that you're able to get your hands on this a little bit. It'd be kind of similar to a just real quick in-class exercise we'll be doing in the future. It's not like a homework assignment. It's just getting your hands on it a little bit. Okay, so let me quit R. And I think that's all I have. Okay, see you next week.